In the last video, we explained how a basic sequence to sequence model works and its limitations. Now, let's look at how a sequence to sequence model with attention operates. First, the encoder processes the input sequence one word at a time, producing hidden states at each step, just like the model without attention. These hidden states are then passed to the decoder. However, instead of using only the final hidden state as the context vector, the attention model uses all of the hidden states. This allows for more flexibility in the context size. So, longer sequences can generate longer context vectors that capture more information from the input. An important point about attention is that each hidden state is most closely tied to the part of the input sequence processed when it was generated. For instance, the first hidden state corresponds to the first word, capturing its information the most. As a result, focusing on a particular hidden state directs the model's attention to the corresponding word. The same applies to subsequent hidden states, even though each hidden state also carries information from the preceding words. Now let's take a look at how the attention decoder works. At each time step, the attention decoder focuses on specific parts of the input sequence using the context vector. But how does it know which part of the input to focus on? This is learned during the training phase, and it's not simply going through the sequence step by step. The model can learn complex patterns. For example, let's consider translating a French sentence into English. After passing the input sentence through the decoder, we enter the decoding phase. In the first step, the attention decoder focuses primarily on the first part of the sentence, outputting the first English word. In the second step, it shifts attention to the second word in the input sequence and translates it. This continues for a few steps, producing a reasonable translation. Then, at the sixth step, something interesting happens. The attention jumps to a word one position ahead in the input to translate one. The input sequence contains donde una epoca más, and in English, the word order changes to just one more epoch. The attention decoder first focuses on more epoch, then shifts back to one, and finally to just. And finally, outputting is never just one more sequentially. This example shows how attention enables the model to reorder words when translating. Learning these patterns from the training data and how attention helps models focus on the right parts of the input at the right time, producing accurate translations. Now that we've covered a high level overview of how attention works in sequence to sequence model, let's dive deeper into the details. We'll use machine translation as our example, as that's the focus of the foundational papers on attention. However, the concepts here apply to many other tasks as well. It's important to note that there are various attention algorithms, but we'll focus on a simple one for this explanation. Starting with the encoder, we'll use a recurrent neural network in this example. When setting up an RNN, we need to specify the number of hidden units in the RNN cell, whether it's a vanilla RNN, LSTM, or GRU cell. Before feeding the input sequence into the encoder, the words must go through an embedding layer, which transforms each word into a vector. Here we can see the vector representation of each word. For simplicity, we'll be using a toy embedding of size 4, but in real world applications, embedding of size 200 or 300 are more common. To avoid cluttering the skin with numbers, we'll represent the vectors with color coded boxes. Now that our words are embedded, we can feed them into the encoder. When the first word enters the RNN at the first time step, it generates the first hidden state. This is called the unrolled view of the RNN, where we can observe the RNN at each time step. The hidden state is stored, and the RNN processes the second word at the next time step. The same process occurs for the third word. Once the entire input sequence has been processed, the hidden states are ready to be passed to the attention decoder. Now let's shift our focus to the decoder. In models without attention, the decoder RNN would only receive the final context vector along with the embedding of the AND token. It would then generate each element of the input sequence step by step. But with an attention decoder, things work a bit differently. The attention decoder can look at both the input words and its own hidden state. It uses a scoring function to score each hidden state from the content matrix. After scoring, each hidden state gets a score. Passing these scores through a softmax function makes them positive, between 0 and 1, and ensures they sum up to 1. These softmax values represent how much each hidden state contributes to the attention context vector, which is generated by multiplying each vector by its corresponding score and then summing them up using a basic weighted sum. While this context vector is key, it's not the final output. In an upcoming video, we'll explain how the context vector merges with the decoder's hidden state to create the actual output at each time step. At this point, the decoder has examined the input word and used the attention context vector to focus on the relevant part of the input sequence. It then generates a hidden state and outputs the first word in the sequence. This is still an oversimplified view, and hence the asterisk. There's another step between an RNN and the final output that we'll cover later. In the next time step, the decoder uses its previous output as input, generates a new context vector for the current step, and combines it with the previous hidden state. This produces a new hidden state and another word in the output sequence. This process continues until the entire sequence is generated. In the next video, we'll cover how the scoring function works, and we'll be covering two important attention mechanisms called the multiplicative attention and the additive attention.